Hi, welcome to a new session of Basic Electrical Engineering. The syllabus, which is designed for Unit 2, it is known as AC circuits, where we have the representation of sine waveform. We have to study about the waveform, its peak value, that is the maximum value, RMS value. Then we have to take the relations of phasor representation and different types of powers like active power, reactive power, and calculating the associated power factor. And this analysis we are going to done with a single phase AC circuits consisting of single resistor, inductor, and capacitor, and the combination of resistor with inductor, resistor with capacitor, and finally with RLC. Then on the application side, we are going to see the resonance effect. What is resonance? And then pertaining to the single phase, we are going to shift our attention to the three-phase system. Here we are going to consider only the balance system. So in this class 1, we are going to take the syllabus in three factors, that is representation of sinusoidal waveform, then what is peak value, RMS value, and what are the phasor representations, then how to calculate the active power, reactive power, and apparent power. And this we are going to do with individual RLC network, and then we are going to combine with RL RC network. We are also going to see the numericals which are associated with this kind of concept. So first we will try to understand what is a sinusoidal waveform. Here you can see a single phase sinusoidal waveform, or it's called as a sine waveform. In figure A, you can see the waveform is represented with T, that is the time period, and the same waveform under frequency analysis, it is denoted by 1 by F. Here you should know that the frequency and time, they are reciprocal to each other. Okay, in general, any quantity, that is the alternating quantity, whether it is in the form of voltage or current, it is represented by a sinusoidal waveform, and the frequency is defined as number of cycles per second, and it is denoted by F, whereas the time period is uh, defined for a complete cycle, that is you have a positive waveform and you have a negative waveform, and it starts from 0, it ends at 2 pi, so this becomes one cycle. And here this particular waveform, whether it is in A or B, it is 2 cycles. Okay, then if at all you go with the depth analysis of a sine waveform, this waveform, the maximum positive value is obtained at pi by 2, that is at 90 degrees, whereas the positive to negative, it is treated as a peak to peak value, and the time period, which is already defined for 0 to 2 pi, it is given by T, and if at all I want to go for 2 cycles, it will be treated as 2T. So for a sine waveform with instantaneous value V, which is given by Vm sin omega t, you should remember this concept in your mind first before applying this concept to the three-phase circuit. Anyhow, we'll apply this single phase waveform to resistor, inductor, and capacitor, and then we'll combine the passive elements. So the phase of a sine wave is the time that has elapsed since the quantity has last passed through 0 point of reference. This definition is taken for phase from a textbook of famous authors, like we have Ravi Singh, we have C.L. Wadhwa for basic electrical and electronics engineering. You can refer to textbooks and you can redefine the definition for phase. Now, what if at all we have two waveforms of sine wave? This is shown in figure 2 as lead and lag of two phases sine waveform. So in the first case, you can see we have waveform VA, VB, and waveform VA and VC. So on the left graph, you can see VB and VA, the green waveform and the red waveform, as well as on the right side, you can see the orange waveform with the blue waveform. Okay, what does this waveform indicates? So the left side indicates the voltage VB leads VA by 5, and on the right side it indicates voltage VC lags VA by 5. So if two waves reach their maximum and zero values at the same time, then they are said to be in phase. whereas the phase difference is used to compare the phases of two sine waves. Here we can see VA, VB, VA, VC are the two waveforms differently, which are representing the phases values. Now, what if we want to calculate the average value of a sine wave? So for this, we have a general formula of averaging the waveform, that is taking the total time period as 1 by t and taking the integral value from 0 to t and taking the value of v of t dt. Here v of t becomes the instantaneous value. For instance, we have Vm sin omega t as the instantaneous value. So if at all I apply the average value for V is equal to Vm sin omega t for integral 0 to t, then the integration will be applied to sin omega t dt. And for this, if at all you apply in general the t value, you're going to get the average value as 2 Vm by pi for only positive half. If at all you take the total time period as t, that is the positive half as well as the negative half, you'll get the value as 0. You can comment in the chat box whether you are getting the same value, that is 0 or not, for one complete cycle. This we are calculating for the half cycle. Now similarly, you can calculate the value of RMS for a sine wave, which is given by the general formula as under root of 1 by t integral 0 to t v square dt. So here we have the value of v, which is nothing but Vm sin omega t. We'll take the value and we'll take the help of the sine square omega t dt, that is nothing but 1 minus cos 2 omega t by 2. This value we are represented by this particular value. And when you take the actual conditions, you're going to get the RMS value as Vm by root 2, which is 0.707 Vm. So once we are done with RMS value and average value, we can easily calculate the form factor, which is nothing but the ratio of RMS value by average value, which is obtained to be 1.11. And we can also calculate the crest factor or the peak factor, which is nothing but the maximum value by RMS value, which it is around 1.414. So these two values are nothing but the important values for a sine waveform, where you can define a sine waveform in terms of its average value as well as the RMS value apart from the maximum value. Now we know how to study a sine waveform. Now we try to apply this sine waveform to a pure resistor. Now the input is V is equal to Vm sin omega t, and the formula for voltage across resistor is given by Ohm's law. I am going to take the help of this Ohm's law for sine wave, and I'll apply the formula of Vm by R for the voltage across resistor, and hence I'm going to end up with the formula of I, which is nothing but Im sin omega t, where Im is nothing but Vm by R. Now VRMS we have already estimated, that is nothing but Vm by root 2, and I'm going to take this Vm by root 2 and I'm going to take this Im value, and if it already you are going to substitute the value of Im by root 2, then we are going to get the RMS value of voltage across resistor. Now you can see a straight line is drawn, that is the voltage is followed by a current I in straight direction. Now these two quantities, that is voltage and current for resistor, it is purely they are in phase form. So this is a phasor representation for single phase AC when it is applied to resistor. Now if at all you calculate the power calculation, the power is nothing but V into I. So I am substituting the value of V and I, that is the instantaneous value of voltage and current. Then I'm going to get this formula, that is Vm Im sin square omega t. With the mathematics, I'm replacing the formula for sin square omega t as 1 minus cos omega t by 2. Hence I'm getting the power value in terms of a constant value as well as the fluctuating value. And if at all I average this power, I'm going to get the value as Vm Im by 2. In fact, I can represent Vm by 2 as root 2 root 2. So it becomes Vm by root 2 and Im by root 2. Hence the power, that is the real power of the pure resistive system, is obtained to be V into I. So these capital letters, you can see they are representing the RMS values, whereas the small v and small I representing the instantaneous values, and the maximum value is represented by Vm and Im. So this is how we can differentiate between RMS value or instantaneous value or the maximum value. So for a pure resistor, the waveform of voltage and current which are in phase, it is shown in this waveform. So this indicates that the voltage source is delivering the constant power to the resistive load connected to it. Therefore, if you combine these two waveforms, we get the power waveform in this fashion. Now, once we are done with the pure resistor, let us focus on pure inductor, where the supply input is AC input, and this AC input develops a back EMF, and the input is Vm sin omega t, but the voltage across inductor from Faraday's law, it is given by L di by dt. With this equation, I am taking di on one side and dt on one side, that is taking the time constant values on one side and variable current value on one side, and I'm integrating this value. I'm going to get the value of I, which is nothing but minus Vm omega L cos omega t. This negative is the resultant of this integration of sin omega t. Now that can be changed to Vm by omega L sin omega t minus 90 of sine, which is nothing but cos. Or I can replace Vm by omega L as Im, and this sign can be replaced as sine omega t minus pi by 2 in radians form. So equation 1 and equation 2 indicates the voltage and current relations of a pure inductor. So the RMS values are used in drawing the phasor diagrams. So we have Im is equal to this value, where XL I am representing omega L and omega is treated as 2 pi f, and reframing the above equation in order to get the RMS value, and therefore concluding that the current lags voltage in a pure inductor by 90 degrees. So this you can see the waveform of equation 1 and equation 2 in this phasor representation. The similar thing, when you calculate the power is obtained to be 0 if at all you take the average value. Now with the conditions of voltage and current waveforms, I'm going to get the power waveform in this fashion, but the average value will be 0. Now you take the example of a capacitor. Unlike inductor, when you talk about the capacitor, we know that the charge across capacitor is CV, and current is defined as the flow of charge, that is nothing but dq by dt, and representing q by cv, I'm going to get the value of I, which is nothing but Im sine omega t plus pi by 2. So with equation 1 and 2, it is clear that the power for the pure capacitive, we are going to get the average as 0, same like as of the inductor, and this is the waveform representation of the voltage and current through capacitor. And once you are done with the voltage and current calculations, we can easily obtain the value of average power, which starts from 0 and ends up at 2 pi, and it's a cycle which is repeated for different values of capacitor. So you can see the current waveform, voltage waveform, and the power waveform, and this is the phasor representation of capacitor voltage. So what is the conclusion? Unlike inductor, here current leads voltage by 90 degrees. So if at all you summarize the resistor, inductor, and capacitor applied to single phase AC input, you're going to get the current, which is Im by sin omega t for resistor. For inductor, it is Im sin omega t minus pi by 2, that is minus 90 degrees. And for the capacitor, it is positive 90 degrees. Means what? For a resistive load, the voltage and current are in phase. For inductive load, the current lags voltage, and for the capacitive load, current leads voltage. Now with this conclusion, let us see some numericals. where you have first example as input supplies 240 50 hertz applied to a resistor of 10 ohms. We have to obtain the instantaneous current and power consumed by the resistor. So for this we take the inputs which is given and then we'll calculate the value of current. Now the formula of voltage, that is instantaneous voltage, is given by Vm sin omega t, and if at all you substitute the value for Im and Vm, we are going to get the value to be uh, that is Vm is 339.4 volts and Im nothing but divided by 10 we'll get the value as 33.94 sine 314.159 t. The omega is estimated over here. This value is given as 50 for frequency f, and this calculation leads to the power which is consumed by the resistor as 5760 watts. Now the same problem, you take an inductor with the Henry value as 0.1. So take the inputs, that is inductor is 0.1 Henry, and calculate the current, that is the current due to the reactive component, that is nothing but 7.63 amperes, and calculate the voltage in instantaneous form, and the Vm is obtained to be V multiplied with root 2 because Vrms is equal to Vm by root 2. Therefore Vm value will be 240 multiplied with root 2, that is 339.4. So that is substituted here. Omega we have already seen from the previous calculation, and I is equal to Im sin omega t minus pi by 2. So you calculate the value of Im, which is 10.79, and substitute here. So the value of voltage and current in instantaneous form we have obtained. So what is the conclusion? Current lags voltage by 90 degrees. Now you take the example of capacitor, calculate the values, and you will come to a conclusion that current leads voltage by 90 degrees. Now once we are done with RLC, let us focus on RL circuit. Once the current flows through resistor and inductor, the developed voltage will be resistor voltage and inductor voltage. So the input is Vm sin omega t, and total voltage is nothing but displayed voltage as VR and VL, that is applying KVL, and the resistor voltage and inductor voltage is given by these two equations in this particular equation. And I'm going to take the current common, and I'm going out with the impedance value, which is nothing but R plus J XL. So the voltage across resistor is in phase with current, whereas the voltage across inductor leads current by 90 degrees. That's good. With this, the actual impedance values taken in the form of magnitude and angle form. So the magnitude is given by Z is equal to under root of R square plus omega square L square, and the angle is given by tan inverse XL by R. When you're going to take the relations of resistor, we know that the VR, that is the voltage developed across resistor, and the current are in phase, whereas inductor, the current lags voltage by 90 degrees. We are going to combine this RL, and we are going to see the resultant, that is shown by this voltage triangle. Then calculating the power factor, which is nothing but the real component by the impedance value. The same thing we will apply for impedance triangle, and we are going to get the waveform for the RL load, which is shown by this diagram. So power calculation, if at all you estimate, we have P is equal to V into I, and this particular Vm Im sin omega t minus phi can be solved with the help of this trigonometry sin A sin B formula, and substituting this formula I'm going to reach with P is equal to Vm Im, which is nothing but cos phi minus cos 2 omega t minus phi by 2, that is the fluctuating component is twice the applied of the voltage frequency, and its average value is 0. So what happens to the actual value of power? The actual value of power is nothing but the real power, which is Vi cos phi, and you can estimate the reactive power with the sign notation, that is denoted by Q is equal to Vi sin phi. Now when you talk about the uh, active power, reactive power, and the apparent power, we are going to get the value for reactive power and apparent power with the help of power triangle or voltage triangle or impedance triangle given by the power factor formula, which is shown by these three triangles. So this is true for RL circuit. Similarly, you go on with the single phase supply applied to RC circuit and then calculate the impedance value, then check the current and voltage waveforms, and you will get a conclusion that capacitor current leads the voltage by 90 degrees, and calculate the actual power, the reactive power and the apparent power, which is given by these triangles, and power factor can be estimated by any of this triangle formula. And then let us go with the examples of the voltage which is applied to a current, and you have to calculate the impedance, phase angle and the power factor and power consumed. Now you look into this particular value. This is given in the rectangular form. Current is also given in rectangular form. So convert the rectangular form to polar form of voltage and current. Then calculate the impedance. And impedance, it is obtained to be 16.12 at an angle 82.87. Now actual value of impedance is 16.12 in its magnitude form, and the angle of power, that is about 82.87. But the power factor can be estimated as cos phi. Apply this phi, that is cos 82.87, you are going to obtain to be 0.124. This is lagging in nature. Now when you calculate the power consumed by the network, you are going to get as 9.99 watts. So this is one example. Another example, you can see a voltage waveform and the current waveform in their instantaneous form. It is given. We need to calculate the power factor and the average power. So for that, take the conditions and check the phase angle between the given input voltage and current, which is taken as a difference of minus 60, but the cost value of 60 is 0.5. Therefore, the power factor will be 0.5, and the average value of power is nothing but Vrms, Irms cos phi value, and that is obtained to be 578.3 watts. In the sixth problem, again you can see a voltage and current waveform given. We need to calculate the reactance, power factor and power. For that, take the voltage and current conditions, take the RMS values of voltage and current, then calculate the impedance value, which is in polar form obtained to be 0.833 at an angle minus 20 degrees. Now impedance has to be represented in ohms. Convert into rectangular form. Then we have the standard rectangular form as R minus JXC. With this, we are going to get the value of resistor, which is 0.783. But the actual parameters, the reactance, that is nothing, the capacitive reactance obtained to be 0.285 ohms. From this, you can also calculate the value of capacitor. You comment in the chat box whether you are able to calculate the value of capacitor or not. Then the power factor is given by cos phi, which is nothing but 0.939. Here it is leading in nature. And finally the power, which is nothing but 56.34 watts. So this is how you deal with the single phase AC circuits, and these numericals, I'm sure that definitely they are going to help you for future calculations. And the next class we are going to see the concept of RLC applied to AC, then the application of RLC as the concept of resonance. Then we'll apply the single phase concept to three phase, and we'll talk about the voltage and current relations in the class 2 for BW unit 2. So I hope you understood this particular session. Please share among your friends, subscribe to this channel.